Okay, today I present these 4 topics. Topic 1, a set spanned by vectors. I present this topic in the last class, but today I want to show you one more example about this topic. Then the second topic from section 4, compute a matrix times a vector. Then the third topic, we can write a linear system as a matrix equation. A times a vector is equal to a vector. The fourth topic, more examples about section 4. Take a review. Some key points from the last class. The first one is a linear combination. A linear combination of this vector, these k vectors, is a vector of this form. A scalar times a vector plus a scalar times a vector plus a scalar times a vector, and so on. A combination of this form is called a linear combination. It is similar to a linear equation. Linear equation is a scalar times a variable plus a scalar times a variable, and so on. Linear equation, right? It is a number. Yeah. An equation of this form is linear equation. Similarly, a vector of this form, a number times a vector plus a number times a vector plus a number times a vector, and so on. It's a linear combination. Now, a B. I use this notation to denote the set of all possible linear combinations of these k vectors. Put all the linear combinations together. I have a set, and I denote the set by this notation. I call this set. I call this set is the set spanned by these k vectors, by the k vectors. Yeah, these are the key points from the last class. Now, topic 1. I show you one more example about this topic. I present this topic in the last class. Topic 1. One more example. Then vector A be 1, -2, -5. I write this vector as a point. Recall that we identify a vector as a point and also as an arrow. A vector A2 be 2, 5, 6. A3 be 1, 2.5, and 3. And vector B, 7, 4, -3. All the 4 vectors are 3-dimensional vectors. So if you plot these vectors, you should plot the vectors in XYZ space. Now questions. A graph this set, the set span by A1 and A2. Let me solve this part first. Solution. By definition, this set is the set of all vectors of the form a scalar, say alpha, times A1 plus beta times A2, where alpha and beta arbitrary. Now, in detail, A1 is 1, -2, -5, plus beta. A2 is 2, 5, 6. A number times a vector is the number times all the entries. So the first term is alpha, -2 alpha, 5 alpha. The second term is 2 beta, 5 beta, 6 beta. Now I add these two vectors. Then I get -2 alpha plus 5 beta, -5 alpha plus 6 beta. So this combination is this vector. A vector is a point. Yeah, this is this point. X coordinate is uh, 2 beta. Y coordinate is, and then C coordinate is this number. Yeah, where alpha, beta arbitrary. Now, let me plot all the points. Pick some special values for alpha. Say when alpha is 0, beta is 0, plugging 0 in alpha and beta, then I see this point is a point in this set. Let me draw. Okay. Suppose here is the space R3, and origin is here. Origin 0 is here. Okay. Then this point is in the set. When I choose alpha 1, beta is 0, then this combination is just A1. Alpha is 1, beta is 0, then we get A1. A1 is 1, -2, 5. Okay, so A1, suppose here, this is A1 here. Yeah, this point represents A1, or you can use the arrow starting from the origin and ending at this point to represent A1. If I choose alpha 0, beta 1, then I get A2. A2 is also in this set. A2, this is A2. 2, 5, 6. A2, say about here. A2, this is A2, this is A1. A2 here. So this point is in this set. We can use an arrow to represent A2. Okay. If I choose, say, some negative values for alpha and beta. Say alpha is a -1, beta is a -2, say for example. Now plug in -1 in alpha, -2 in beta, then I get this point. -1, -5, right? And then -1, 2, -10, so -8. -1 here, 5, -12, so -7. So this point may be here. Yeah, it's here. So if you plot all the points in this set, all the points, you will see form a plane. The plane contains the origin, contains this point and this point. Or in other words, the plane determined by the origin and A1 and A2. Yeah. All the points together is a plane. A plane in R3. A plane in R3. So these two vectors, A1, A2, span a plane in R3. The graph of this set is a plane. Is a plane. Now, this is question A. Now, question B. Question B. B. A graph. The set spanned by A2 and A3. Solution. A2 is 2, 5, 6. Right? A2 is 2, 5, 6. Yeah, here. A2, 2, 5, 6. A3, 1, 2.5, and 3. A2, A3 is 1, 2.5, and 3. It is easy to see that A2, this vector, is 2 times A3. Now let me plot A2 and A3, 3-dimensional vectors. So use XYZ plane. Suppose here, this is R3 here, R3. And origin is here, this point, origin, right? Origin here. Origin is a 0, 0, 0. Yeah. Suppose this vector is A3. A3. Oh, A2 is 2 times A3. So A2, this vector has the same direction as A3, but twice the length of A3. So A2 is this vector twice the length of A3. Yeah. This vector is A3. This is A2, A2. Now this time, these two vectors span a line. If you plot all the points in this set, all the points form a line determined by A2 and A3. The line surpass the origin. Yeah, this line. All the points form this line. This is the graph of this set. Because A2, A3, they are on a line, so they span also a line. This is question B. Now, question C. Question C. We have 4 vectors, A1, A2, A3, and vector B. determine whether vector B is in the set spanned by A1, A2, and A3. Whether vector B is in this set, that means that whether B is a linear combination of A1, A2, and A3, because this set is the set of all linear combinations of A1, A2, A3. So this question amounts to the question whether B is a linear combination of A1, A2, and A3. Now, to answer the question, we need to solve this equation. X1 will be determined plus X2, A2, plus X3, A3. If we can determine scalars X1, X2, X3, then B is a linear combination of A1, A2, A3. If this equation has no solution, then B is not a linear combination of those three vectors. Okay, now I solve this vector equation. Vector equation actually is a linear system. How to see a vector equation is a linear system? Write the equation in detail. Okay, so, in detail. Vector B is 7, 4, -3. Vector A1 is 1, -2, -5. A2 is 2, 5, 6. And then A3 is 1, 2.5, and 3. Okay, now let me compute the right-hand side. The right-hand side. X1, scalar, times a vector. So scalar times all the entries. X1, not X2. Times X1, 5, X1. X2 times this vector is X2 times all the entries. 5, X2, 6, X2. And then X3 times all the entries. 3, X3. Now, make a sum of the three vectors at the corresponding entries. So X1 plus X2, X1 plus 2X2 plus X3. Then second entry is -2 X1 plus 5 X2 plus 2.5 X3. And -5 X1 plus 6 X2, 3 X3. Now, this vector is equal to this vector. That means that their corresponding entries are equal. So we have a linear system. Compare the first entries, then we have this equation. X1 plus 2, X2, X3 is 7. Second equation from the second entries. negative 2x1 plus 5x2, 2.5x3 is 4. The equation is from the third entries. Negative 3. Yeah, a linear system. So this vector equation is a linear system. Now, to answer whether or not this vector equation has a solution, I need to solve this linear system. Solve this linear system, I form augmented matrix. Augmented matrix. Okay. Augmented matrix is a 1, 2, 1, 7, negative 2, 5, 2.5, 4, 6, 3. Yeah. Then separate the last column. Last column is the right-hand side. The first 3 columns is coefficient matrix. Yeah, this part is a matrix of coefficients of the linear system. About this augmented matrix, did you notice that the first column, 1, negative 2, 5, negative 5, actually is this vector. Yeah, the first column, 1, negative 2, negative 5, actually is this vector. This vector is A1. Yeah, A1. The augmented matrix, first column is A1. The coefficient of x1 in the vector equation. The second column, 2, 5, 6, actually is this column. This column is A2. The coefficient of the variable x2. Yeah, A2. A2. The third column is the 1, 2.5, 3. Actually is this vector. This vector is A3. The coefficient of x3. Yeah, A3. A3. The last column, right-hand side, actually is this vector. Vector B. Yeah, this is a vector B. Vector B. So a vector equation is a linear system. How to write down the augmented matrix of the linear system? Easy. Put A1 first, then A2, second column, A3, third column, and then the last column is B. This is augmented matrix. Okay, now to see whether or not the linear system has a solution, solve the linear system by reducing the augmented matrix into epsilon form. Okay, now let me solve on next page. The augmented matrix is 1, negative 2, negative 5, and 2, 5, 6, 1, 2.5, 3. Then right-hand side, 7, 4, negative 3. Okay. Okay, now step by step. Positive 2 times row 1. 0, 9, 4.5, 18. And then positive 5 times row 1, add to row 3. Then negative 5 is gone. 16, 8, 32, 32. Then I scale row 2, by dividing row 2 by 4.5, 2, 1, 4, and then scale row 3, divide the row 3 by 8, then 2, 1, 4, 2, 1, 4. Forward, I am performing forward elimination. Then negative 1 times row 2, add to row 3. Negative 1 times row 2, add to row 3. Row 3 becomes a row of zeros. Now this matrix is in epsilon form. Okay, now I can answer whether or not the linear system has solutions. Look at the bottom non-zero row. Yeah, the bottom non-zero row is this row. Yeah, this row. Because this row is not a row of the form 0, 0, 0. Then non-zero. Right-hand side is non-zero. The bottom non-zero row is not in this form. Then the linear system must have a solution. If the bottom non-zero is in this form, the linear system has no solution because the non-zero entry here is right-hand side. Left-hand side is 0. Okay, now the linear system has solution. The linear system is consistent. Therefore, the conclusion, the answer to part C is yes, this vector is in this set, the set spanned by these 3 vectors, because the vector equation has solution. Yeah. This is one example. So let me finish this topic with this example. This topic, I present this topic in the last class. Okay, now second topic. The formulas to compute a matrix times a vector. Topic 2. Topic 2. Compute a matrix times a vector. A matrix times a vector, the result is a vector. The formula is the definition, or the definition is below. Let suppose A be an M by N matrix. In detail, this matrix has M rows and N columns. The 1-1 entry is A11. Say 1-2 entry is A12. And the matrix has N columns. So the last entry is A1N. This is row 1. Row 2. After 2-1 entry, let me denote it by A. At the 1-2 entry, let me denote it by A12. 2-2 entry is A22 and A2N, and so on. The matrix has M rows. So row M, the bottom row, first entry is AM1, AM2, and AMN. Yeah. Let me denote the first column. Yeah, first column. Each column is a vector. The first column, let me denote it by A1, arrow. The second column is a vector. Let me denote the vector by A2, arrow, and so on. The last column, let me denote it by AN, arrow. So I cut the matrix in columns. Each column, actually, yeah, each column is a vector. This is a vector because each column has how many entries? M entries. So each vector, each column is a vector in ROM. ROM, yeah, a vector in ROM. This is a matrix A. Matrix A. Now, vector V. I let vector V be how many entries? Vector V should have M entries. Okay. V1, V2, V1, V2, Vm. They are all numbers. Okay, scalars. Okay, M vectors. Okay, now I can define. Now I define A, this matrix, times this vector. Okay, yeah. The formula is A times V. This vector is a linear combination of the columns of matrix A with the weight, with the entries in vector V as the weight. That means A times V is a vector. Which vector? This vector. Scalar V1 times vector A1 plus scalar V2 times vector A2, and so on. The last term is scalar Vm. Vn. Oh, no, not Vm. Sorry. Vector V should have n entries. Vn. Okay. So vector V is a vector in ROM. Okay, not in ROM. Okay. Now the last term is scalar Vn times the vector An. This is the definition of a matrix times a vector. A matrix times a vector is a vector. It is the linear combination of columns of matrix A. Let me show you one example. Okay. Let me put a remark here first. Remark. Okay. A times V, a vector, is defined or computable only when the number of columns of A. In this case, the number of columns of A is n equals the number of entries in the vector V. Yeah, the number of entries in vector V is also n, log m, okay? Okay, now let me show you one example about how to use this formula to compute A times V. Take a look. Example 1. Say compute 1, 2, negative 1, 0, negative 5. Here is 1. This is a 3 by 3 matrix. Now, compute this matrix times this vector 4, 3, 7. Yeah. By definition, a matrix times a vector is a vector. Is linear combination of the columns and use the entries in the vector as weight. That means that 4, this number 4 times first column plus second entry in the vector times second column. And then 7 times the third column. Third column. Okay, now 4 times this vector is 4, 0, 8. Then plus 3 times this vector is 6, negative 15, then 0. Plus 7 times this vector, 7. Now add these 3 vectors by adding the corresponding entries. 4 plus 6 minus 7, number 3. 0 plus negative 15 plus 21, 6. And then here is 50. Done. Finish. This vector is this matrix times this vector. This is part A. Part A. Okay, part A. Now, part B. Part B. 1, 2, negative 1, 0, negative 5, 3, 2, 1. Yes. This matrix has 3 columns. This is a 3 by 3 matrix, 3 columns and 3 rows. Now times this vector. Now this time, the vector has only 2 entries. 4, 3. Now this time, because the number of columns in the matrix is not equal to the number of entries in the vector. It's not equal. Now this time, this product is not defined or not computable. You can have a try, okay? Try, yeah. A matrix times a vector is linear combination of the columns. So 4 times first column. And 3 times second column. How about the third column? Nothing times the third column. Not computable, not defined. So when number of columns not equal to the number of rows, not computable. One more, say C. 1, 2, -1, 0, -5, 3, 2, 0, 1. Now this matrix has 3 columns, but the vector now has 4 entries. 4, 3, 7, 0. This time, this product is not computable, not defined. Have a try. Linear combination of the columns. So 4 times first column. Then 3, number 3 times second column. And then plus number 7 times the third column. Then 0 times low column. This time, not defined the product or not computable. Not computable. Yeah, this formula, let me call this, I'll give a name. Formula, this equation, formula 1 is one formula to compute A times a vector. If I write this formula in detail, then I will have a second formula to compute a matrix times a vector. Okay. Okay, now let me write this equation in detail. I want to have a second formula. Okay, A times V is V1, A1, V2, A2, Vn, An. Okay. In detail, A1 is the first column of matrix A. So A11, A11, A21, AM1, right? The first column of matrix A. Now, A2, second column of matrix A. Second column is A12, A22, AM2, and so on. The last term is Vn times An, the last column. Last column is A1n, A2n, then AMN. Okay, now let me compare V1 times this vector. It is A11 times V1, A21 times V1, and so on. AM1 times V1. plus the second term, A12, V2, A22, V2, and AM2, V2, and so on. The last term, V1 times Vn, this number, scalar, times all entries. Okay, now I sum up all the vectors by adding corresponding entries. So the first entry, make a sum. A11, V1 plus A12, V2 plus A1n, Vn. Second entry, A21, V1 plus A22, V2, A2n, Vn, and so on. The last entry is AM1, V1 plus AM2, V2, and so on. AMN, Vn. Yeah. In detail, A times V, it is a vector. Which vector? This vector. So from this vector, we can see that A times V, the first entry is this number. This number is a sum of products. The product of A11, A12, A1n, this is the entries from the first row. And then times V1, V2, Vn, entries from the vector. So actually, the first entry is row 1 of A times vector V. Row 1 in detail of A, A11, A12, A1n times vector V, V1, V2, Vn. This vector times this vector means A11, first entry times V1 plus A12 times V2 plus A1n times Vn. So A times V, first entry is row 1 of matrix A times the vector. Row 1 times the vector means sum of products of the corresponding entries. Similarly, second entry, A times B, second entry, it is row 2 of A times vector V. Vector V. Okay, so row 2 of A is A21, A22, A2n. Vector V, V1, V2, Vn. Yeah, this means row 2 times vector V means the sum of the products of corresponding entries. Entry 1 times entry 1, A21, V1 plus A22, V2, and so on. A2n times Vn. Okay, now in general, A times V, its ith entry is row I of matrix A times vector V. It is row I. The first entry of row I is AI1 times V1 plus AI2 times V2 and so on. AIN times VN. Yeah, let me copy this equation on a new page. Okay. This is the second formula to compute a matrix times a vector. Okay, now let me give a name to this new formula. Okay, we call it row vector rule to compute a matrix times a vector. The formula is a matrix times a vector is a vector. The ith entry is equal to row I of matrix A times vector V. In detail, row I is AI1, AI2, AI. Suppose that A has n columns, so the last entry is AIN times vector V, V1, V2, Vn. Row I times row vector times a column vector. That means that first entry times first entry plus second entry times second entry plus the last entry times the last entry. Yeah, second formula to compute A times B. Let me call this equation. Give a name. Equation 2. Equation 2. Okay, now example about this new formula. Example 2. Example 2. How about let me use the matrix and the vector in example 1. Yeah, here. Let me use this matrix and this vector. Now I compute this matrix times this vector by the new formula. Okay. 1, 2, level 1, 0, level 5, 3, 2, 0, 1, times 4, 3, 7. A matrix times a vector is a vector. The first entry of the vector is by the new formula is row 1 times the vector. That means that first entry times first entry, 1 times 4, plus second entry times second entry, 2 times 3, plus third entry times 7. Negative 1 times 7. Yeah. A times B is a vector. The first entry of the vector is this number. Now, second entry is row 2 times the vector. Row 2, yeah. Row 2 of the matrix times the vector. That means that first entry of row 2 times first entry of the vector. So 0 times 4 plus second entry times second entry, negative 5 times 3. And then third entry times 7. Now, the third entry in this vector is row 3 times beta V. Row 3. Yeah. Row 3 times beta V. The answer is first entry times first entry, 2 times 4, plus second entry, 0 times 3, then plus 1 times 7. Okay, now the result is 4 plus 6, 10 minus 7. So number 3. 0 times 4 minus 15 plus 21. It is 6. Here, 8 plus 0 plus 7, 15. So this vector is this matrix times this vector. I got the result this time by using the second formula. This is topic 2. What is topic 3? Topic 3. Also from section 4. Write a linear system as a matrix equation. Matrix equation, yeah. A matrix times a vector is a vector. Yeah. This equation is a matrix equation. Now I can write a linear system as a matrix equation. Let me show you one example. Topic 3. Topic number 3. A linear system can be written as a vector equation. Okay. And as a matrix equation. Let me show you one example. Say, take a look at this example. Example 1. Okay. 3x2 minus 6x3 plus 6x4 plus 4x5 is negative 5. Second equation, 3x1 minus 7x2 plus 8x3. 5, 8, then 9, 3x1, 9x2, 12x3, 6x5, and 15. Yeah. A linear system of 3 equations in 5 unknowns. Now, let me first write this linear system as a vector equation. Okay. Put left-hand side into a vector. Okay, the vector. a vector, and also put the numbers on the right side into a vector. Then we have this equation, right? This vector is equal to this vector. Now, let me split the vector on the left side into a sum. Okay, now from here we get, let me continue on a new page. Now we get split this vector into a sum. Then I get 0, 3, x1, 0, plus 3x2, 7, and then plus 6, 9, x4. All the entries about the same unknown. 4, x5, 8, x5, 6, x5. And then equal to the right side. The right side is 5, 9, 15. Okay, now in the first vector, x1 is common to all the entries, right? The first entry is 0 times x1. So x1 is a scalar. I can take x1 out. So x1 times 0, 3. Take x2 out. 3, 7, 9. Take x3 out. 6, 8, 12. And then x4 out. And then x5 out. Yeah, the variables, all the unknowns, they are all scalars. So I can take scalar out. Yeah, this is a vector equation. Vector equation. So a linear system can be written as a vector equation. Now, let me further write the vector equation as a matrix equation. Okay, now let me form a matrix first. Let me let matrix A. Yeah. First column is this vector. 0, 3, 3. Second column is this vector. 3, 7, 9. Third column, 6, 8, 12. Then fourth column. No, not yet. Fourth column. Now the fifth column. 4, 8, 6. And also I put the unknowns x1, x2, x3, x4, x5 together into a vector. This is an unknown vector. x1, x2, x3, x4, x5. Yeah. The right-hand side, let me denote the right-hand side by B. By B. Then the vector equation, the left side of the vector equation, actually the left-hand side of the vector equation is A times X. By definition, what is A times a vector? Linear combination of the columns of the vector. Yeah, you see, first column of matrix A, second column matrix A. Yeah, this equation, the left side is linear combination of the columns of matrix A. And the coefficients, the scalars are the entries of this vector. So actually, the left side is matrix A times vector X. Is equal to right side, vector B. Yeah, vector B. So this equation is a matrix equation. Also, this is this linear system. Linear system. The reverse is also true. A matrix equation can be written as, by the definition of a matrix times a vector, can be written as a vector equation. A vector equation further can be written as a linear system. Let me, based on this example, let me make a summary. A summary. Okay. In summary, a linear system with the augmented matrix we have a linear system whose augmented matrix is this. Okay. First column, A1. It is a vector. First one column is a vector. Second column, A2. And say how many columns? N columns. AN. Yeah. So these columns together is the coefficient matrix of the linear system. Now separate with from right hand side. Right hand side is B. Right hand side is also a vector. Okay. A linear system whose augmented matrix is this can be written as the following vector equation. The vector equation. Okay, which vector equation? Okay. The unknown. Suppose the unknowns is x1, x2, xn. Okay. So it is x1 times first column plus x2 second column plus xn column n is equal to right hand side. A linear system can be written as into this vector equation. Further, this vector equation can be written into a matrix equation. Okay. 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 Further, okay, the vector equation is the following matrix equation. Okay. A times X is equal to B. Okay. What is A? Where A is first column A1, second column A2, and AN. Yeah. A is coefficient matrix. X the vector of unknowns, x1, x2, xn. How about B? B, right-hand side vector. Yeah. So A times X, by definition, Formula 1 today is linear combination. So this vector equation, the left side actually is this matrix times this vector. Therefore, a linear system can be written into a vector equation, can be written into a matrix equation. The reverse also true. A matrix equation can be written into a vector equation. A vector equation can be written into a linear system. Yeah, they are the same. They are the same. I don't think I have time to present topic 4 today. Yeah, topic 4. Let me see. More examples. Yeah, let me present this topic in the next class. Next class is Tuesday next week. Okay, now let me stop here today.